All right, in step 5, you need to write the equation F equals ma for each mass. Here, be careful. In this equation, both force and acceleration are vector forms. Okay, the vector notation there. So let's do that for each mass. We can start with mass A. For mass A, and I have all the forces plus, so we have NA plus WA plus FA plus FTA. This is sum of the forces equals MA times AA. Okay, so this is a simple application of the equation F equals MA. And here, since we have multiple forces in the free body diagram, therefore it's a sum of all the forces. And we're not done yet. So I want you to do is go back to step 3 and look at all the ij components for the forces and substitute them inside of your equation here. So here I would write out all my, what is my NA, WA, FA, and FTA. And okay, I will just simply copy what we have there. So my NA gonna be negative NA I, big I, plus WA has two components, which is MA G cosine theta I plus G MA sine theta J. And we have two more forces, minus mu mu NA plus FTA. This is on J direction. This is on J direction. Okay, and those are all the forces in terms of I and J components. Equals MA times AJ. Okay. So that's how you do F equals MA. Make sure you plug in all the vector form of forces and the vector form of acceleration into this equation, and you will end up with this long equation with I and J components inside. And what you can actually do is you can organize this equation by put all the I's components together, all the J components together. Okay, let's do that. Let's combine all the I components and J components. For I components, we have negative NA plus MAG cosine theta. This is our I component. And plus our sum of all the J components. Here we have MA sine theta minus mu NA plus FTA minus AA. Here the MAAA come from the right hand side of the equation. You simply put that on the other side of the equation. That's a Y component. So here we should have J. That's a J component, sorry. And this I and J plus something J goes to 0 because I simply put A times AAJ to the other set of equations, so we end up 0 on right hand of the equation. So now let's look at this expression here. We have something I plus something j, it's 0. And that tells us this vector is 0. And then we can start to extract scalar equations from I and j components. For I components, we only have one I, right? So negative mu, oops, that's not mu, that's NA. Negative NA plus A G cosine theta is 0. And for J component, we have A sine theta. I think we're missing a G here. G minus mu NA plus FTA minus AAA equals 0. Okay, now you have two equations. This is the first two scalar equation. You have this called this equation 1 and equation 2. Now, once you end up with some scalar equations, you can start to solve unknowns. And if we just look at these two equations, let's start with equation 1. And what we will end up from equation 1 is we can find out what is this NA. NA is a normal force of block A, which is the first thing we try to find is the unknown. NA is AG cosine theta. That's one of the answer. Okay, from 2, what can we get from 2? Equation 2. Instead of equation 2, FTA is the only unknown, so we can put FTA on one side of the equation and put everything else on the other side of the equation, which is AAA minus AG cosine, that's going to be sine theta, plus mu NA. Of course, you can plug in NA from the first equation here. But here from second equation, we can find the expression for FTA. We do have unknowns here. For example, this AA is an unknown, we don't know. So we cannot solve FTA directly, but this equation is going to be helpful. So you're going to just put that here, and let's continue writing F equals MA equation for mass B. Remember, we just finished F equals MA for mass A. You need to do F equals MA for mass B as well, since you need to do this for